Okay, 5.4 is all about addition and subtraction of polynomials. So what we're going to do is we're going to break up polynomials into a couple different sections in Chapter 5 so we can learn how to add and subtract them, we'll learn how to multiply them together, and we're going to learn how to divide them. And that's going to help us a great deal when we hit college algebra. So first, what in the world is a polynomial? Well, the word prefix poly means many, like many parts. A polynomial is a shape that has many sides, or a polygon. So a polynomial is an expression, think like an equation without an equal sign, an expression that is the sum of a finite number of terms of the form ax to the n for any real number a and any whole number n. So that is a really mathy way of saying you have this long string of mathematical terms where you have exponents possibly, but those exponents have to be whole numbers. That's really all it says. So polynomials will have many, many parts. The next little table setup that I have here, I'm specifying that there's 3 different polynomials that have special names. They're monomials, binomials, and trinomials. You don't really have to know that. I just wanted to make sure it was apparent what I was discussing because you will hear me say binomial quite a bit in this class. You may hear me say monomial, but really binomial is the one that we use the most. A monomial has 1 term in it. That's all it has. Mon means 1. So we have 1 term. A binomial, think of like a bicycle. Bicycles have 2 wheels. Binomials will have 2 terms. And trinomials, like a tricycle or a triangle, will have 3 terms. After that, we just generally call them polynomials if they have 4 or more terms. But every once in a while, I will say a trinomial or a binomial. Very rarely will I say monomial. And then next to those, I did put a non-polynomial column as well because I wanted you to see that there is some differentiation over here on what specifies a polynomial versus a not polynomial. So while this looks like it has 1 term, the problem lies here with our exponent. Our exponent is 1/2. We learned in 5.1 whole numbers start with the number 0. Go 1, 2, 3, 4. They don't include fractions at all. So this one is not a polynomial simply because of the exponent that lies in our variable. If we look at the example that would lie with the binomial, well, we have 4 plus 1 over x. This is from 5.2. So we can write 1 over x as 4 plus x to the negative first power. That is a negative exponent. Whole numbers don't include negatives. So again, it doesn't actually follow the definition of a polynomial. Same thing for this third option. We have this negative exponent in there, and so thus we do not have a polynomial. Polynomials will have nice whole numbers, 0 through infinity, in terms of their exponents. Some of your problems, you will need to determine the degree of your polynomial. This is not hard. This is looking at the variables within your polynomial. So if you only have a monomial, so 1 term, like 2x to the 3rd, the exponent on your variable is the degree of your polynomial. That's really what you're going to look at almost every time going through these. So we would say this is a 3rd degree polynomial. And you may be asking, why is that important? Later on, when we solve this, these actually help us to determine how many solutions we could possibly get out when we solve these different types of equations. So knowing the degree is helpful. There's also a lot of theorems that come in with this that allow us to solve our polynomials in a lot easier ways. If you have 2 or more variables that are being multiplied together, that isn't written there, but it definitely needs to be stated, that are being multiplied together, then you're going to take the sum of your exponents. So here we still have just really 1 term, but it has more than 1 variable at play because we have these 2 different variables. And so we have 2 different exponents. So in order to find degree of this term, we would have to add these powers, giving us a 5th degree. Something I want to make really clear here is that if this said 4x squared plus y to the third. Can you see that? Yeah, barely. If it said this, so notice it's the same format, but we have an addition sign here separating our variables. If that was the case, this would be degree 3. You will always take the highest degree if you have multiple terms that have multiple different variables. This one that's in pencil is degree 5 because it's being multiplied together. That's why we will add them. Otherwise, you look for which variable has the highest exponent out of your entire expression, and that will give you the degree of your entire polynomial. Almost all of your problems will be single variable, meaning you're not going to have a lot with x's and y's at play where you're finding the degree. You may encounter a couple. Most of them, if you're dealing with terms that have x variables, you're only going to have x variables, because we will learn to solve single variable problems, not double variable problems, for a little while. Okay. The last one is when you are given a polynomial. That is crooked. Sorry. If you have a polynomial, so you have more than one term, which is what this example in green was. This is a polynomial. It has more than one term. Then you just look at the degree of the highest exponent. So I do give two different examples here, just so that we can be really clear on this. The first one is x squared minus 4. So the only term that has a variable at all is the x squared. And so we use the 2 as our degree. This bottom example, we have x squared y to the 4th plus 2x, plus 3. Well, this term has an x squared. This term only has an x. This term also has that y to the 4th attached to it. This one acts just like the 4x squared y to the 3rd up here. We're going to look at this term to figure out the degree of our entire polynomial. 2 plus 4 is 6, so the degree is 6. There is a little column note over here. This goes back to 5.1, where the degree of any number is 0. And the reason why that kind of goes back to 5.1 is if I have the number 5, and you're looking at that and you're thinking, okay, there's no exponent, or excuse me, there's no variable there, so there's no exponent. That's true. But we could write this like this. We won't ever, but we could. And this is a good way to visualize why this has a degree of 0. From 5.1, we learned that anything raised to the 0th power is what? 1. So this is saying 5 times 1, which is 5. This is why any whole number, any number that doesn't have a variable attached to it, will have a degree of 0. Just in case you do have one of those pop up on a homework assignment, you know what the degree is, and this is why. It's not just you have to remember it and it's just the rule. There's actually a mathematical reason why. Are there any questions at all about how we determine the degree of a given polynomial? Okay. Well, this section, 5.4, was all about adding and subtracting of polynomials. So, how do you do that? Well, you add or subtract the like terms. One of the reasons we kind of start focusing on the degree of the polynomials is really to focus in on like terms. So, like terms have to have two things in order to be like terms. They have to have the same variable, and they have to have the same power on that variable to be like terms. Can you see me? Okay. 2x and x squared. These both have the same variable, but they do not have the same power. We could not add or subtract these together any further than what they already are because they do not have both. So these are not like terms. If I had 3x to the fourth and x to the fourth, I can combine those because they do both contain x's to the fourth. And so I could combine those further. So these are. If you have terms with more than one variable, they have to have all the same variables with all the same powers. So these are really close. We have a 4x squared y and a 4x squared. I still could not combine these using like terms because they don't have the y's in common. So they have to have exactly the same variables with the same exponents in order to be like terms. Chapter 2 in this book also talks about like terms and combining like terms. I want to say it is 2.1, could be 2.2. I think it's 2.1 though. There is a lecture video also available on my YouTube site for all of those chapters because those are covered in Math 20. And so if you do end up needing any additional resources, my Math 20 lecture videos are a great source of review as well. So that's what we're going to do today with the adding and subtracting of polynomials. We're going to look at polynomials and we're going to add and subtract the like terms together in order to simplify them. One thing I really want to make very apparent is in this section, we are dealing with expressions. Expressions don't have equal signs. Some of you may be really tempted to set these things equal to 0 or equal to 1 to try and solve for the x. That is not what we are doing. We are just simply going to take these long polynomials and try and write them as small as possible, and that's it. No solving. We will not know what x is today. So don't be tempted to do that. All right. Hold on. We are going to combine using addition and subtraction. A lot of times they will put the entire different expressions in parentheses. That's just to help you see the different things you are adding together. You're taking this first expression, everything inside this set of parentheses, and we are going to add to it this whole other expression. We're taking a trinomial and adding another trinomial to it. You don't have to leave those parentheses in there. They're just grouped. Sometimes it'll just be a long string of different terms. Everything's going to work the same way. What we're going to do is we're going to look at the different terms and see which ones are alike that we can actually combine together. Because that's how we add and subtract using like terms with these polynomials. So if I'm looking at these, the first term that I hit is 5x squared. That has an x squared term. So then I'm going to go through all of my other terms and look to see if I have another x squared term. I do. So I'm going to take 5x squared plus 6x squared. When you add or subtract with like terms, you're just adding or subtracting those coefficients, the numbers. So 5 plus 6 is 11. The variable stays the same. Then I move on to my next term. I have a negative 3x, so I look for another x term. And I have a minus 4x. Negative 3x minus 4x would give me a negative 7x. And then my last term in each of these parentheses is my constant or my whole number. I have a negative 1 plus 7, which will give me a positive 6. That's all you can do. I can't combine the x squared term to the x term. Yes, they have the same variable, but they have different exponents. So that's as far as I can take it. One good habit to go ahead and get into is always writing your polynomials in descending order. What I mean by that is you write the term that has the largest exponent on the left, Then you write the next term, then the next term, and the next term, all the way down until your constant term. This is just best practices. What this will allow you to do is later on when we actually start solving these, you have it perfectly set up and ready to solve. So while you could type this into Pearson as 6 plus 11x squared minus 7, you could reorder these and it wouldn't count you wrong. This is the best practice. Write them in descending order. I think all of mine are already written in descending order for the examples. Any questions on what I did? Okay. B, we have our first polynomial or trinomial expression. We have a minus this time, and then we have our second trinomial expression. When we are dealing with subtraction as our operator, my number one suggestion, if it has these parentheses around your second expression, is to distribute that negative. And if you had me for any other class before, you've probably seen this table, but just as a reminder, when you take a negative times a negative, what are you going to get? Positive. And if you take a positive times a negative, you'll get a negative. Negative times a positive, you get a negative. And a positive times a positive gives you positive. Basically, if the two signs that are being multiplied together are the same, you get a positive output. If they're not the same, you get a negative. This also holds true, this table, if you change this multiplication into division. That also works. So the reason why that's going to come into play, here in the first expression, nothing's changing. I'm just going to drop those parentheses. That's all I'm going to do. So I'm writing everything as it is. And then I'm going to distribute this negative. The distributive property is where you take what's out front times everything inside. So if there's 2 terms inside, you're taking it times the 2 terms. This one has 3 terms. This x squared is positive, but this sign is negative, meaning I will have a negative x squared. Negative times the negative 3x will give me a positive 3x. Negative times the positive 4 gives me a negative 4. I always recommend doing this because here's what I see happen 95% of the time if a student misses this problem. They will distribute that negative to this x squared and not to any of these other terms, and then their entire answer falls away. It doesn't work then. So we have to distribute that negative to every single thing. And I draw the arrows every time I distribute anything whenever I do my lesson so that you can physically see what it is that I'm doing. And that helps me also to remember to do it. Once you've distributed, you work it the same way as if you're adding. I look for my like terms. I have 3x squared minus x squared. So that'll give me a 2x squared. Then I look over and I have a negative 2x and a positive 3x. That'll give me a positive x. And 5 minus 4 gives me a plus 1. Now, you won't always have 3 terms. I think all of these do. No, the next one only has 2 terms. Sometimes you might have an x squared term and a constant, and you won't have an x term. That's okay. It just depends on what your problem is stating. Are there any questions about how we do either of those? Yes?
For me, I like the parentheses there, so when I go ahead and distribute, I keep the parentheses there, but change it to a positive.
That is fine. Yes. If you want to leave parentheses like this, make sure you put a plus out there, because if not, then what you're stating is you're multiplying. But yes, that is totally okay. One thing about me, I don't know if I've said it in this class, I have a lot of classes. I'm not a my way or the highway professor. So if you have a method that you really like and it's mathematically sound, I'm totally cool with you using it. I will never come up behind you and be like, why didn't you do it my way? I will show you lots of different ways, as many ways as I can on a lot of things, just so you have lots of different ways to attack these problems. Because sometimes you might want to distribute it, sometimes you might not, sometimes you want to use the parentheses, sometimes you might not. And so everybody's different, and everybody's brains are wired differently. So I definitely want you to do whatever makes the most sense to you. Okay? All right, let's look. We got two more. This one's got fractions. I put the fraction problem in here on purpose. Most of the time students don't like fractions, and that's okay. But fractions are not going to go away. So you need to be comfortable with fractions. At the beginning of this book, chapter 1, the very first section that we start with in Math 20 is 1.3, which is all about fractions. I actually take 2 whole days to cover fractions. And so if you need more fraction review on how to find common denominators, how to simplify, how to multiply or divide them, or anything to do with fractions, I highly recommend looking at my 1.3 lecture video for beginning algebra, because it's got everything you could possibly need there. But the way we do fractions is the same way we do our polynomial addition and subtraction. We still are looking for like terms. This term has an x and this term has an x. And luckily for us, they have common denominators already. So we can just add them. When you add or subtract fractions, you have to have common denominators. And so it's a good thing we don't have to combine these. We're combining our 2 x terms. They both have denominators of 8. So when you add fractions, you add the numerators, which is 1 plus 3. That'll give you 4. You leave your denominator alone, and you write your variable out to the side. There are fractional buttons within the Pearson site so that you can type these in. Then I look at my whole number portion, or my constant terms. Again, we're super lucky that while we have fractions, both of these have like terms in the denominator. We have 16 and 16. So I'm taking 5 minus 1, which will give me a positive 4 over 16. Now, if you type that into Pearson, you will be counted wrong. Anytime your problem has a fraction, you always want to ask, is it simplified? If it's not simplified, you have to simplify it. And the way you know a fraction is simplified or not is you look at the top, the numerator, and the denominator at the bottom, and say, do they have anything in common? Does 4 and 8 have anything in common? Yeah, because 8 is 4 times 2. So that means there's a 4 on top and a 4 on bottom, which would leave me with a 1 over 2x. I do the exact same process over here with 4 over 16. Do 4 and 16 have anything in common? Yeah, 16 is 4 times 4. Again, the 4s would cancel, leaving me with 1/4. If you didn't know the 4s came out, you could always say, well, 4 and 8 are both even. Even numbers mean 2s come out. 4 and 16 are both even, so 2s would come out. That would leave you, again, with even over even, so you could pull additional 2s out. As many steps as you need to take, that's fine. One thing you don't want to do is this says 1/2 x plus 1/4. You don't want to put 0.5x plus 0.25 into your Pearson. Don't rely on those calculators to do that. If it wants a decimal, Pearson will ask for a decimal. Otherwise, you want simplified fractions. And again, this is Math 20 1.3. Or 1.3 in your textbook is a place you can go and just look at the textbook if you really want to. Fractions are not going to go away. So if you've never felt comfortable with them, this is the class to feel comfortable with them. So they're going to pop back up in college algebra as well. You don't want to put it in decimal form. No, you want to leave it. This is the final answer. The boxed in is the final answer. I'm trying to think if we actually use decimals in here. Not for a long time, as far as I can remember. Fractions are actually way more user-friendly in terms of solving mathematical things than decimals are, and so that's why we like to leave things in in fractional form. This last example I put in here because I wanted you to understand that reading it when it's written this way means something a little bit different than the way that we had it before. If it says subtract this polynomial from this polynomial, since it's subtraction, it's really important which one we put first. Short example, 4 minus 5 is -1, but 5 minus 4 is +1. The order makes a lot of difference in subtraction. We get different answers. And so when I look at this, do I put this polynomial first or do I put this polynomial first? And how do I know which one goes first? All the other ones were already written out for us, but this one has words. So what do you think? Which one goes first? Does the 3x squared one go first or the -x squared one go first? That's exactly right. This one is first. This word from is super important. It's telling you where you're starting from. So we're going to start from this term. Now this one is just like example B. I'm going to distribute that negative inside of the second set of parentheses so that I don't have to worry about forgetting it. This first polynomial expression doesn't change anything, so I just rewrite it. Negative times a positive means I have a negative. Negative times a negative means I have a positive. Negative times a negative means I have a positive. Then I do my combining of like terms. I'm going to scroll up so it's higher for you guys in the back. Negative x squared minus 3x squared will give me a minus 4x squared. Positive 3x, positive 5x will give me a positive 8x. Then I have 10 plus 3 is 13. Again, we cannot solve, we cannot combine any further. That is the end of that problem. We simplified, we subtracted, that is all.